Yeah, thanks so much for the invitation to come talk. So let me just set up the problem. So we're interested in counting the number of 3 progressions in some set, and we're just assuming that it's somewhat large. So the theorem that we have is this one. Okay, so I'm just looking at this linear equation and counting the number of solutions to it with all x, y, z, and a. And we're saying that when a is dense, we get this many solutions at least. And then, so certainly if this number is larger than n, then we find a non-trivial solution. So something that I want to do very quickly is like we're going to stick with statements of this form so that we can just forget about trivial solutions. And instead, I want to just reformulate the problem as saying we're just trying to find as many solutions as possible. And okay, so this is certainly plenty. And we can do slightly better in some other groups. So we can ask this analogous question here for subsets of vector spaces over finite fields, and then we get slightly more. So this is d to the 9. Okay, so this parameter d, I'm going to stick with that to measure the density. It's like talking about the entropy deficit of A. And then you can see that the number of 3 progressions we get, it's like polynomial. Okay, so the entropy deficit is translating to this loss that's like polynomial in the exponent in the number of 3 progressions. So I'll also note this one in third setting. So here we're just in an arbitrary abelian group. And here we get basically the same answer as we get in the integer setting. This was this follow-up work due to Bloom and Sisask, where they just showed that you can carry out our argument very nicely in an arbitrary group using Bohr sets in like the way that you would like. And my main point about all of this is that the techniques are very uninterested in like the specific choice of group, essentially. So because of that, we're going to focus on this guy here for the talk, just because it explains the essential ideas. And then there's a few small details that change when you change the group, but roughly we're doing the same thing in spirit. Okay, so let's see. so let me say, like at a high level, what something that you could call the analytic approach to the three progression problem, and it's right now can just state it sort of for any group. What is the plan? The plan is to find a subset A prime with the right number of three progressions, right? Okay, so like the expected number that you would get for a typical like random set. So that, you know, you could say that's roughly this number. Okay. So we'd like to find like a nice subset that's, you know, pseudo-random in a sense. It's giving you roughly the right number that you would expect. And certainly, right, so for this to be sensible for our original task, you'd like this to be large as possible. And then how are you going to actually find it? Well, you could do various things, but typically the plan is you could describe it like this. We're going to look at subsets of the form A intersect B, where B is structured. And then here's where I want to say, like, this is the only kind of part of the plan that depends on the group. So maybe it's a subgroup, or maybe it's like an approximate subgroup, like a four set, or generalized arithmetic progression. Okay, so if you're working in a group like this one that has plenty of subgroups around, then this will be fine. Like you can execute this plan and try to find a subgroup to find this subset A prime that has the right number of three progressions. You might be in a group, you know, just like a cyclic group of prime order, and then there's no subgroups lying around. So this is just not sensible. There's no subgroups to use. You need to use some sort of approximate subgroup in that case. But so yeah, in spirit, what we're doing, it changes very little, but that's why in the talk, I just want to focus on this case where we're looking at some group that has plenty of subgroups lying around so that we can execute this plan as painlessly as possible. Subgroups are just a bit nicer to work with than approximate subgroups. So I want to move on to explaining sort of the criteria we're using to decide when A prime is good and when it's likely to have the right number of solutions to this equation. And so we said that the number of solutions we're asking for, you do get it when A prime is actually random. So what we're looking for is like a set that's behaving pseudo-randomly in some way. And here's the specific way that I want to quantify that. So yeah, so again, the setting is that you have this subset of an abelian group. And then what I want to do is draw some random variables, X and Y, at random. Okay, and then we're going to look at the sum of these two independent variables, and we're saying A is pseudo-random when this is very nearly uniformly distributed over the group. So yeah. Okay, so here I've drawn the situation that I'm talking about. I'm taking these random variables, X and Y, considering their sum. And what I want is for the probability distribution that is associated with the result of that to be near the uniform distribution on G. So here is 1 is the uniform distribution on G. And here we're like pointwise close, upwards and downwards from the uniform distribution. And the point is that in this setting, like, so this is an extremely favorable setting. It won't be quite this favorable in general, but in this setting, what is the point is that for any set C, so okay, the number of solutions to A plus A prime equals C with A prime. So this is what we wanted. It's like 1 plus epsilon times. C. Yeah, thanks. Okay. So sure, that's explaining why at least this very strong notion of pseudorandomness is sufficient. And what is the point for our original application is that we're just thinking of this specific set C. So set of elements 2A, where A is in A. Right, in that case, this is exactly counting what we care about, the number of 3 progressions. Okay, now I should say, yeah, we are able to tolerate a tiny bit of error here. So let me change the drawing here slightly and say maybe that on some very small set, you do go out of bounds of this small 1 plus or minus epsilon band. I'm going to say this is 2 to the minus k fraction. Okay, then what kind of guarantee do we get here? Then for any C that's not too large, so I'll say like this, it's fine. All right, sorry, not too small, so 2. Okay, so certainly we are still happy with this situation. We're losing like a factor half in the number of 3 progressions. Isn't a big deal at all. So why is that? I'm saying if you were looking at any set C, sort of the worst case is that C completely contains this bad region. But C is not too small. It's like twice the width of the bad region. So on this region outside the bad region, you're still getting the number of 3 progressions you expect. Okay. So finally, I can just say, like, what is the main result, or not the main result, maybe the main theorem of the lemma, or theorem of the paper is for to the n. The setup is the same as always. We have A in our group. It has entropy deficit at most D. Then we have that either this function A star A is near uniform. And I'll quantify that like this, and we'll come back to talk about what that means exactly in a second. Okay, and or we get a density increment onto some subspace of small codimensions. So
move the board up and down if you don't want to crouch.
So yeah, I guess I forgot to say, for this talk, there's only two important parameters. There's D and K. I'm going to keep them separate while we talk about things, but at the end, like for the application, right, you want to set K's like D plus 1. So this is getting us, you know, what we wanted. We're getting like roughly A cubed over G. Like I said, what was the goal? When you set C to be equal to the set, and this set is of size like 2 to the minus D essentially. But yeah, so for the talk, I will try to keep them separate. I think it's a little bit clarifying. This epsilon parameter matters very little. It's always just going to be some small constant like a tenth. And it's like not growing with anything, like not growing with D or K or anything. So, okay, so this is the main point, and then I'll just talk briefly about why this suffices to recover the theorem I claimed at the beginning. Okay, so again, what was our plan? Is that we had our set A, and we're trying to identify some subset where it's good. And when the current set we're looking at is not good, we're going, I mean, that's like the complement of this case. It's this case. We are going to take a density increment onto a large subspace. So that's looking like this. And then, you know, if this subset of A is still not good relative to the new subspace, we look at a further increment. Okay. So, and next, what are we doing? We're passing from A to some subset A1. And the point is that the relative density after T steps it's like grown exponentially in t. So okay, so in particular, it's not possible to be in this case too many times in a row. Like after t steps, we have this density, the density is bounded by 1. So we learned that this procedure terminates by this many iterations. Okay. And then our final codimension of this final subspace inside our original set, right? It's like t times so doing it t times, and then each time the codimension is bounded roughly by 4th power of d times the 4th power of k. So ultimately, we're finding this good subset A prime. And yeah, so what is the size of A prime? So A prime is roughly so for our application, right, we're setting k is like d plus 1 or something. Okay, so all I'm trying to show you is like specifically how you're recovering this, what I quoted at the beginning, that, where we're getting this dependence d to the 9 in the number of 3 progressions we're getting at the end. Okay, so yeah, this should be basically the whole story, assuming you believe this theorem, and then mostly for the rest of the talk, we're going to just talk about how to prove this. So this is like capturing the whole thing that's important. This is just doing the density increment. Okay. Okay, so let me say this. I would actually like to handle an even smaller case. Specifically, we're going to talk about F2 to the n. Now, the 3 progression problem doesn't make much sense in this setting. But this statement does. Like this statement is certainly sensible in F2 to the n. And this is going to introduce some like very minor simplifications that'll just be convenient for us. So yeah, we'll talk about this theorem is like the main goal of the talk, and we'll do it in F2 to the n. And okay, also this is like about as far as I can get without going over some really tiny details related to like notation and conventions. So I'm sorry about this, but like the alternative if we don't renormalize things is that we're carrying around like various normalization constants for the rest of our lives in all the expressions that don't really mean anything. So I just need to take a couple minutes to specifically talk about some normalization conventions. So so this is specifically what I mean by this K norm, is that we're taking an expectation over the group of the kth power, and then we're going to be interested in density functions, which are just non-negative functions with this normalization. And I'm given a set A, then I also want to use the letter A to denote the density function, which is the uniform density function on A. So that's this function. So then also note that if A has this size, then like the entropy deficit of A is captured by the infinity norm once we normalize the one norm to be one. So. Okay. And then, okay, we're interested in like the correlation between two real value functions. And then I want to say that we have this set up so that if you put a density function or in the first position, well, in either position, but if you have a density function here, then right, by definition, it looks like this. But you can reinterpret this as sampling from your density function and then evaluating G where you on that element. And then so here is our normalization convention for convolutions. And then also I want to note, like, you can reinterpret this. If you have a convolution with a density function, also think about it differently like this. Okay. And okay, close to the end here. So my point here is that we have everything normalized correctly so that if you take the convolution of two density functions, you get another density function. It's like one of the main motivations for setting up everything up this way. And also, yeah, specifically, we have this interpretation that if you're drawing X from density A, Y from a density B, then, and these are independent, then X plus Y is distributed according to the probability density function A convolution B. And then finally, I have like two pieces of made up notation that we're going to use in a second. Okay, so this is the theorem restated. The only thing that's changed slightly is that using this notation we just introduced to capture the density increment, like to quantify it slightly more analytically. And then I actually want to change this even more. So we actually proved something a little bit stronger than this. So we proved the following. Should get a density increment of the convolution of A with A. And I'll just describe briefly why that's like only stronger than what we talked about a second ago. So but yeah, okay. So basically just by averaging, like we were saying that this quantity is large, so it's large on average over these shifts A. So what is this saying? It's saying for some translate B prime, we're getting a density increment onto V prime. Okay. That's why this is sufficient for what we wanted at the end of the day. I think this formulation is really nice because the assumption and the conclusion are both about the convolution A star A now.
The word affine still to be in there, or do you want to get rid of that?
Sure. Where are we talking about now?
So on the top board, it says some affine subspace. Do you want that to be an arbitrary, a true subspace now, or do you want it still to be affine?
I guess I think it's more than I know. It's
subspace.
sorry.
I think it can make it a true subspace.
But positivity, it's not important. But
Yeah, maybe not immediately, but sure, I guess. Okay, so now I'm going to move on to the proof outline of this. And like, how does the proof go? Well, we're proving this by contradiction. So we're assuming that that A star A is not near uniform, that we have some deviation from uniform to at least epsilon. Okay, and then like, here's how I would imagine the proof, although I would, we'll state it a bit more precisely in a second. This is roughly telling you that we have a high entropy set C witnessing this deviation epsilon on average. Okay, and here are the 3 steps of the proof. So firstly, I want to say that I actually want to witness a deviation upwards. This is, saying that it's witnessing a deviation downwards or upwards. I specifically want to witness a deviation upwards to get started. Okay, and then second step. Is that we're going from this like arbitrary witness of a deviation upwards to a witness with like some small amount of additive structure. It's like a convolution of some large set with itself. And then like the thing that's degraded slightly is the entropy. So the entropy deficit is somewhat larger, but not by too much. Okay, and then finally, go from here to what we wanted. Is that we're witnessing this deviation upwards with a very highly structured set. V is a affine subspace. So that's the conclusion we were after. And again, the thing that we have lost a little bit of it is the entropy. So V is the entropy deficit of V compared to V is slightly smaller. So yeah, for these last two steps, you can see as we go downward, what's changing. We're increasing in the structure of our witness, and we're losing a little bit in the entropy of the witness. Okay, and then so this last thing is a small caveat. So actually, this convolution needs to be a robust witness. Which by that I mean that this deviation it witnesses, I wanted to witness it usually, not just on average. Okay, so we actually need, we need this stronger condition if we want to go from this line to this last line. And then if you really want like the most compact description of this whole thing, you could get I can give you one in terms of this notation over here. That we're starting with this assumption that A star A is not near uniform. Okay, and then the first assumption is to convert this two-sided deviation into just a one-sided deviation with the arbitrary witness of small entropy deficit. Then we get this witness with a small amount of additive structure, and then we get this witness with a large amount of additive structure. Okay, yeah, so this is the whole argument, and then I can also give you like a name for each of the pieces of it. How do we do this part? This is like one, this is spectral positivity. Two we're doing by sifting. And three by almost. So these steps 1 and 2 are where we like the main contributions to the paper, and then here we apply some tools that were in the literature, like sort of directly. And then, yeah, mostly the paper is responsible for introducing these first 2 points. So, okay. Might be a good place for like a break, a 5-minute break, maybe, if you wanted to try to do that. Yeah, okay, yeah, so we'll have a 5-minute break and then come back. And then for the rest of the talk, I'm going to go over these 3 steps. That'll complete the proof. So. Sure. Sounds good. So for the rest of the talk, we're going to talk about these 3 steps, like in backwards order. Okay, so yeah, to start with, we need this kind of formulation of almost periodicity. The main thing going on here is like I would say it's fair to say it's like 90% powered by the Sisask lemma, but this is like bootstrapped with Chung's inequality to get almost periodicity on a structured set B. And the idea to do that first appeared in the work of Sanders. And okay, so what is it saying? That if you have a large set B and look at its convolution with itself, then this is very close in statistical distance to the same density function if you average out along a large subspace. So there's a like small caveat here that it's not quite this strong, but this is how I would encourage you to think of it at least. But the technical point missing here is that actually, why am I saying, I mean, if you're familiar with the statement, it just doesn't look like this. But if you have two density functions and you look at the one norm distance between them, we have this dual interpretation, just the max over bounded functions. Okay, and the point is that the subspace V depends on this witness F. So for certain applications that you might be concerned about that, but in our case, that we're going to talk about fixing the function first, and we're not worried about whether or not the subspace depends on F. So for us, like basically, it's no different than this statement here.
Just to be clear, the statement you wrote up there is not true, right?
Well, I have a star here. I don't know if you can see it, but
Okay.
Yeah. So I actually think it might be true. I don't know if it's true. Yeah. Yeah. So this is explaining this caveat. Okay. And then for us, we can like summarize pretty succinctly, like, well, how is this important for us in this corollary? So for any bounded function, and then what I'm gonna do is use this notation here. It's telling us that this like perp norm, where you're talking about witnessing with subspaces, is roughly at least this star norm, where we're witnessing with large convolutions. I guess some dependence on epsilon here. I guess I'll write. Okay. Yeah. So for us, this is why we're interested in this, and like also, this is an aside. This is also why like Sanders was interested in this. Like this captures the reason he wanted it as well. So this is for Sanders's quasi-polynomial Freeman-Russe theorem in F2 So the main step of this theorem, I'm not going to say like totally what it is, but the main claim that's needed is to say that if B is large, then there is a subspace that's large, and it's like mostly contained in the sum set B plus B. So it's like the majority of it lies in this sum set. Okay, so that's what the main thing he needs to prove. And so I'm claiming that this follows like very quickly from this fact for a particular choice of function f. So anyone have an idea for the choice of function f? It's just the indicator function of the sum set. So in this case, then this quantity is 1 as witnessed by, right, B star B itself, right? So B star B lies completely in the sum set. Okay, so this quantity is evaluating to 1, and then applying this, we're getting that there's a subspace that witnesses this inner product like roughly as well. For some, large subspace of this bound on the codimension that's like d to the 4. Okay, so I'm saying this is a proof of this statement, which I'm saying is the main thing needed for Sanders' quasi-polynomial Freeman-Russe theorem in the case of f2 to the n. And the one reason I say this is that this is sort of like inspiring for our argument. So how are we going to use this? So instead, I want to use this statement on a particular choice of function, which is going to be like a super level set of, so I'm going to consider this sort of function. Right, where we're looking at the super level set of A star A. It's fairly analogous to this setup here. So remember, our goal was to show that if we have a set B, that's B is large, and that this is robustly witnessing deviation upwards from 1, then this is the kind of conclusion we were after. And I'm claiming that one way to restate this is that for this super level set function, like it suffices Okay, so here, like probably you noticed, but really all these epsilons are changing by like a tiny constant fraction or constant amount that I haven't been writing down the whole time. So sure, maybe I would say, yeah, our goal is to maybe obtain this actually, which we're certainly also fine with. Maybe I should leave this on the board for now. Yeah, so let me try to justify why. I mean, this is simple. Basically, the connection is just this calculation here. And what kind of, okay, maybe I want a 2 here as well. So what do I want to say? Well, let me just write the entire calculation, I guess, and then talk about it. Yeah, so sorry, maybe something I forgot to remind you of. I guess it's up there somewhere, but this is part of our assumption as well. Okay, so sorry for this mess here, but hopefully it should be fairly straightforward. Like if you understood what I was saying about how Sanders's argument used this corollary, we're using it in a similar way. By assumption, we have this robust witness that lies mostly on this super level set of A. So like only one minus, or like only a tiny fraction is falling outside of it. Okay. So we're using that here to get a lower bound on this quantity. Okay, and then we're using this lemma to connect this step, and then this first step is like straightforward. Okay. Fine. So any questions on this? Like this is like the end of this third step written up top here. Try to clarify anything that seems unclear. Anyone?
What is F from this?
Yeah, F is the same function. I was just trying to skip writing again. It's the same function. Yeah. Freddie, any way I could help you out? Okay.
This L1 thing is really smart. I was trying to figure it out. Thinking about it, it's the function, the choice of F is given to you naturally by duality. It's yeah.
I see. Okay. All right. Fine. And then if everyone's happy with this, then I'm going to move on to this second connection. So what, like this is saying that you know, we can get to our final goal of a density increment if only we can find a robust witness for A star A. And to find one, we're going to use sifting. So to start with, let me just say, I want to consider this question without the additive structure at all. If you just have an arbitrary density function and you make this kind of assumption, can you find a high entropy robust witness for it with no regards to what the witness looks like? So that certainly we would like to say that we can do. And it's fairly simple that you can. So let me see. And it's important that we have also a simple explicit description of it. Okay, so I just want to say let d of x be a density function. And then I want to consider the density function, which is the unique density function, which is proportional to the kth power of d of x. So that's, I'm going to use this notation for that. So this is actually normalized so that it's a density function. Okay, and then the claim is that, this is the claim, that it's a robust witness for D being roughly as large as its own K norm. So let me write that like this. Okay, so what is this saying? I'm looking at an arbitrary density function D, and then I look at the sub-level set defined relative to the K norm of D. And then I have this density function here that's escaping this sub-level set. It's like mostly completely lying outside of it. Okay, so sure, this is happening in general, and the idea is to think about what is it telling us in our case. It's especially useful that we have this explicit description. Right, okay, so we're starting from an assumption. That looks like this. which is saying that this deviation is witnessed by some high entropy density function, but like importantly, it's witnessed specifically by one that looks like this. So, how do I want to write that? So this density function is a robust witness, and then the only thing missing is like, is it actually, does it have the structure that we wanted? Okay, so it has, I guess we can check that it has the entropy we wanted. That's like an easy calculation. So this guy is the most. Okay, so we can find this explicit density function. It's a robust witness. And then the only question is like, does it have the kind of additive structure we want? So not really, at least not right now. It's not a convolution itself. It's the kth power of a convolution. And then the question is like, how close is that to what we actually needed? Is that reasonably useful as well? I should probably stick with F2 to the end, actually, because I'm like forgetting minus signs everywhere otherwise. I'll say that this statement, but now that we're past number 3 here, everything that we're talking about like applies more generally to an arbitrary finite abelian group. The only thing missing is the fact that I'm like not making a distinction between plus signs and minus signs. That's the only reason I'm care about that we're in F2 to the n anymore. Okay, so here we get to like the heart of the argument we need for this second step is the sifting lemma, which is telling you that this witness is actually, it has enough structure that we're able to get the kind of witness that we wanted at the end of the day, which was a convolution of 2 large sets rather than, the kth power of a convolution of 2 large sets. And here I've stated it somewhat abstractly. This time I want to use F to be like a sub-level set. So F, you would pick F to be something that looked like this to infer the statement that we want now. So my plan now is to go into the proof of the sifting lemma. Before that, I'd like to ask if there's any questions with like the setup or why it's useful for us. So I can just summarize. We were looking for a robust witness of a particular form that was high entropy. I can just write down a robust witness. Like this is a robust witness. It's like possibly not of the form that we wanted. So then the last step is to apply the sifting lemma to obtain some subset A prime that's itself fairly large. That's like as good of a witness as D. Okay, and then there's some like flipping between sub-level sets and super-level sets to facilitate. Okay.
Maybe I forgot exactly what you meant by robust witness.
Sure. So a robust witness. Okay, so this is saying that yeah, A star A, B minus B prime is like at least 1 plus epsilon with high probability.
That's what you mean by robust witness of the form
Okay.
star B. What do you mean by robust witness that isn't of the form B star B?
Sure. Yeah. So for a general density function, I guess I mean this, that it's like, well, almost the exact same thing. Where did my eraser go? Right. Like if you sample according to D, then A star A with high probability. Okay, so certainly you could also phrase this in terms of some inner product with like a super level set or yeah.
You see, so thinking of the k norm being large is saying that almost always, you know, the bias of A star A in the upwards direction, or like on a large set or something, and D is going to be the large set where that's true or something. So
You're asking about.
so I'm trying to interpret again, just like it's a robust witness, but what is it a robust witness of?
Oh, sure. Yes. Yeah. Like it's a robust witness of the deviation upwards from the uniform distribution.
Okay. Gotcha. Okay. Thanks.
Yeah. So I mean, the alternative would be that it just witnesses this deviation 1 plus epsilon on average. It could like have some very rare, very large deviations upwards. And I'm saying that doesn't count. That's not useful for this third step. Like the, you know, almost periodicity needs a stronger input than that, which is why we're using sifting to find this. Okay, so yeah, I was going to erase this, so I guess that's fine by now. So now I'm just talking about the proof of the sifting lemma. And I think that like for this argument to, you know, it's sort of combinatorial, it's fairly useful to switch to a different normalization. So this is like the representation counting function. Which is counting the, well, okay, I can stick with this, I guess. The number of representation of an element X as a sum of two elements A and A prime in the set A. And like, right, so what this is proportional to this quantity we've been considering the whole time, the density function A star A. Okay. And fine, so what is the next part of the setup is I just need to define, well, for S, which is like a K minus 1 tuple of points, we're defining this subset of A as the intersection of A with some translates of itself. Okay, and now here's basically the proof, is use the identity for the kth power of this representation counting function. And we can just expand it as a sum of the representation counting functions of all of these subsets for every choice of S. Okay, and then like then the last step is like making an appropriate choice for S. And then, yeah, right, so for the sifting lemma quoted over there, we're taking A prime is AS. Okay, so I would say this, it is fair to say that this is the whole proof. Like, I'll give you a small justification of this identity in 1 second. And then the rest of it is like dealing with accounting, I mean, I don't know, to switch from this to this, it's like a non-trivial exercise in checking normalizations and things, but otherwise we're just using the first moment method in a sort of standard way to pick a good choice of S that's giving us, like, basically, because we were expanding this term out as some weighted sum of these guys, we were able to pick a good choice of S. So, balancing both of these things that we care about, which is the size of the subset A prime, and then also like this error term here. Okay, so that is roughly the proof, but except for this identity. So I'll try to give you a small sketch of the identity itself. so somehow I think it's easier to see, or like to make this calculation work out in this like equivalent dual form, where we're gonna prove this equality like for every function g. So certainly, like by interpolation, that's sufficient. Okay, so in this form, what can we do? We write first step. Just using the definition of this representation counting function, we're like unpacking just one of these k factors and writing it out like this. Okay, now at this point, I want to give you a different interpretation of this quantity. Which is a sum over, I'll call it E at this point. Okay, so there's maybe, you would have to think about this for a little bit. There are some like combinatorial arguments hidden here. But analytically, this is what I would like to state it as, because now the final step is to just expand this this product of k minus 1 summations as a summation of products. And then that gives us the final result. So let's see. Yeah, finally we're getting S1 up to Sk minus 1. Okay. So yeah, the result of these 3 steps is giving you this equivalent form for every function g. So that's proving the identity. So that's the last thing I have to say about sifting. So any questions on that or on anything else?
Sorry, I think you said it and I missed it. When you said make a good choice of pass, that's just some choice where this thing is large. So
So we're balancing 2 things. Oh, well, okay. The way I have this set up, I'm making a choice so that this is small, because right now I'm picking F to be a sub-level set. But then the other thing that I need is that I want A prime to be somewhat large. So I'm balancing both of those things. And then, yeah, there's like a first moment method kind of argument. Okay. Okay, so, sorry, this is item 1, I guess. Now we're going to talk about just this last part where we need to go from our assumption, which is about like the two-sided deviation from the uniform, to we need like an upwards deviation. Okay, so here is a picture of two potential situations where you could imagine like this is A star A, maybe it looks like this, maybe it looks like this. Okay, I'm arguing that, well, it's very important for us that it looks, that it doesn't look like this, okay? Like, and my point is that even, say this deviation downwards from the uniform distribution, maybe it's even structured, like maybe you could even argue that you could, if that in this situation, you can find a large subspace V, maybe by sifting plus almost periodicity, maybe you could argue that, where you're actually witnessing this downwards deviation. Well, that's not giving you a density increment, okay? Like, so even if you could do that task, you carry out the rest of the arguments in this downward direction, then it wouldn't give you anything useful. Like, we want to witness an upwards deviation. Okay, so in fact, you could like kind of summarize the entire density increment framework in a black box as saying, okay, what can we do if we're unsatisfied with our current set, and that this convolution doesn't look like the uniform distribution? Well, the only thing we can do is like squish down the deviations that are going upwards from uniform. That's the only tool we have. So certainly somehow that needs to be sufficient to also control like the downwards deviations. But what I'm trying to say is that it's very important for our story here that there are just no examples that look like this. That's what we're about to prove. Is that if you have this convolution A star A, here I'm using the fact that we're in F2 to the N, so plus signs are the same as minus signs, then you can't have a substantial downward deviation without like also having a substantial upwards deviation somewhere else. So then what do? Then like, in this case, we can find a large subset V here and find a density increment. So certainly super important for the whole story. Now it turns out like the actual argument for this is like super simple, way shorter than, I mean, the sifting is not too long either, but it's really something I can write like all the way out on the board very easily. So I'm saying for density functions of this form, a set convolved with itself, somehow they never look like this, they only look like this. And how am I quantifying that? Just by a simple statement concerning the odd central moments. So this expectation is non-negative for all odd integers. So that's the claim, and it's like it's giving you what I'm saying we needed to connect it to this form. I guess you need a little bit of an extra argument, but essentially this is what you need to show this phenomenon is happening, and that's really the main point. So like just one other way of thinking about this. So what is this saying? Basically, this deviation downwards, the p norm of it is always bounded by the deviation upwards. For roughly all p, right? There's enough odd integers that like basically you are getting this for every p. Okay, so that's the quantification of this downwards deviations and entailing the existence of upwards deviations. And then how do you actually prove it? That's simple. So then I just want to look at the Fourier coefficients of my density function. So since it's A convolved with itself, it's this the squares of the Fourier coefficients of A, which are non-negative. Okay, and then I just want to write D out as its Fourier expansion. Now, because D is a density function, then its trivial Fourier coefficient is just 1. Okay, so then when we look at this centering of D around 1, that's just this expression without the trivial term. And then what, okay, so the main point is that even this centering is still spectrally positive. So we started with something that had only non-negative Fourier coefficients. We considered the centering. Still, it has non-negative Fourier coefficients. Okay, and then at this point, I'm saying it's easy to just like compute this quantity exactly and give you a Fourier analytic expression for it. So yeah, let me do that. Okay, so we're just seeing, that we can give an exact expression of this, and it's just a summation of these terms. All the terms are non-negative, so certainly overall this quantity is non-negative. Okay, and then this is like a special case of the fact that if you had any p spectrally positive functions, they could be different functions, then they're non-negatively correlated with each other. So if you took their expectation of the product of all of them, that'd also be at least their individual, or at least the product of their expectations. So that's a more general fact, but anyway, for us, that's like the end of the story. So this is quantifying the analytic behavior that we needed, that downwards deviations entail the existence of upwards deviations. And then we're just verifying it here that we have this property by like a direct calculation using the fact that Fourier coefficients are non-negative. Okay, so that's all I had to say about spectral positivity. So any questions on that?
So I missed, what's the logical deduction of the K-norm inequality?
Yeah, okay, fair enough. That, like, you could get lots of ways. I guess I'm saying from this, you can get it just from like a pruning argument that looks like the proof of the Paley-Zygmunt inequality, if that means anything to you. But I'm saying, like, yeah, mostly once you have this fact, it's some just calculation to translate that into a fact about the K-norm. Like in our paper, we do it with this like slick way using a binomial expansion. It's not so necessary. You can also just, I mean, sorry, I don't know if that gets like the best parameters. You get a slightly worse dependence on epsilon if you do this other idea I said. But I'm saying, like, okay, we could go through it maybe.
Maybe it's helpful to just write down the lemma for real value random variables, right?
Sure. So yeah, that sounds fine. Yeah. So maybe I'll do that here. I mean, that's just kind of writing down the thing I'm claiming, but fine. Yeah. Okay. So, right. So if X is a random variable, so we're assuming this, and then we're assuming this. Then this implies that okay, yeah, I guess this also catches like another small lie here. Hopefully this doesn't bother you too much, but this K, like the K we're getting at the end is not like the exact same as what we had before. It's like changing by this small constant factor epsilon. Okay,
Epsilon.
sure, great. Okay, so any other question on this stuff? Okay, well, that is like the end of the important stuff. I can talk to you with like 10 minutes. I can just say a little bit about not the analysis, but just like what is the density increment procedure look like for the integers. So the thing that we had to invent is like kind of elaborate in a sense. It's done very cleanly in this like follow-up note by Bloom and Sisask just for arbitrary groups. And in that case, they're just incrementing on Bohr sets in like the standard way that has been happening for a while. But what do we do in the integers? So firstly, I want to say, I want to handle like a more general problem. I want to say that I have a set like in Z to the R for some small dimension R. And then again, I'm assuming the density, some lower bound on the density. And my goal is to just say that here, like this set has many solutions to x plus y equals 2z, just like before. Now this like equation, you know, so linear equation over CR. Okay, so I'm saying that here, whenever R is somewhat small, as well, like we need a bound on D, a bound on R, and then we get some number of, like a large number of solutions to this equation. Okay, so this is a slightly more general problem that's like facilitating the following density increment procedure. So our theorem here is that either, firstly, the number of solutions is roughly okay, so here we're getting a density increment. It's like a fairly liberal interpretation of what a density increment is. So what does it entail? It is a subset A prime, and then a map from A prime into, well, firstly, let's say this, into ZR prime. So I'm allowing the dimension to grow slightly, and more specifically, it's into some cube, like the same as before. Okay, and then we need to control various things. So what are we getting? We're getting like, well, firstly, we're getting an actual density increment. So yeah, I'll say, oh. Hold on. Okay, so firstly, the map is a Freidman homomorphism of order 2. In particular, it's an injection. And the reason for this is I'm saying like we're not getting any new solutions to this equation in 3 variables than we had already. Okay. And then secondly, we're getting a density increment. So A prime in the new space it's like 1 plus epsilon. Okay, and then thirdly, we have like a bounded size loss. And then lastly, we have bounded dimension growth. I think that it's everything that we had needed.
We have prime isomorphism or
What's up?
prime homomorphism doesn't need to be injected, right? It could just be a linear map or something to a smaller.
It does need to be injected because that, like, if it's a K homomorphism, then it's a K minus 1 homomorphism, and like a 1 homomorphism is exactly an injection. Anyway, we do require it to be an injection anyway, but yes, I think that does imply that.
Sure, probably it's one. It's sort of like you just map everything to a single point. That's a prime homomorphism, but not prime isomorphism. Yeah. Like a prime isomorphism onto its image or something. I don't know. GDK.
I mean, maybe the order 2 is something that you want to define more carefully, or
Oh, sure. I mean, I was kind of just saying it for the benefit of anybody who already knew about it, but I guess I could talk about it. I mean, yeah, so specifically, what am I asking for here? Like, I said it in words. I just don't want, I want, you know, what do I want? This is specifically the actual, like, exact feature that I want the map to satisfy only if okay, so that's what I'm saying. I'm using, I mean, this isn't exactly equivalent to this, but if you don't know what this means, this is specifically what I'm asking phi to satisfy is that in the image, I'm not getting any new solutions to this equation. Oh, I guess, sorry, maybe I want the 2 on the outside. Why? I'm not getting any new solutions that weren't already there. So like in particular, this is a sensible way to like lower bound the solutions you had in your original set.
There's a nomenclature dispute, but that's okay.
Sorry?
There's a nomenclature dispute, but that's okay. Yeah.
Oh, okay. I see. Okay, well, sorry. Okay. Yeah, maybe that's all I wanted to say. Thanks everyone for listening.
More questions? In the spectral positivity step, you're not just using that density function is supported on A plus A. You're really using the convolution, right? It's false. The exact claim you would need if you just had an arbitrary density function supported on A plus A.
Yeah, yeah. I mean, that's certainly. Well, okay, right. Like a really bad example.
You get some inequality, but not strong enough.
Like so, A plus A could be the whole group, right? I mean, in that case, certainly no. You're not getting anything. You know, getting like no kind of guarantee at all. Like if you have the whole group, then you know I can just give you this density function. It's uniform on a set which contains almost everything, except for it's missing some set of density 2 to the minus k, and then like this is some horribly small number that's doing nothing for you. Okay.
Can you maybe say a second about the in both talks you've pulled all over our eyes about the difference between A star A and A star minus A. Can you say sort of a couple of words about?
Sure. Yeah. Yeah. There's. I mean, I can just show you exactly what the claim is. It's that itself is very simple. I just tried to omit it. It's not so important, but so this is actually true for any 2 density functions, A and B. You would look at the K norm for some even integer K. Then this sort of, we call it a decoupling inequality. It's like applying Cauchy-Schwarz in the Fourier space to get this.
The star is the,
Yeah, and this is talking, yeah, this is like the convolution with minus signs, okay. So this is what we need, right, for spectral positivity. And this is like the quantity we care about, like A star A. So I assume, you know, this is large, which implies that this is large. That's fine. That's the missing step regarding that.
More questions? Well, let's think again.